So last time we had been talking about the problem of a particle in a one-dimensional square well. And so we had a potential that looked like this as a function of x. Okay, and here's a point L over 2, and here's a point minus L over 2. And the potential looked like this, that it was some constant value V0, then it goes down to 0, and then it goes back up to V0. Okay, so this level here is the potential V0. And so this is describing V of x. And then the Hamiltonian was p squared over 2m plus V of x. And in solving this, we found it useful to define several quantities. One was k equals square root of 2m times the energy eigenvalue over h bar. And the other was kappa, which was square root of 2m v0 minus e all over h bar. So these quantities, k and kappa, both have dimensions of length. And so then we found it convenient, or we will find it convenient, to define versions of those same variables that are dimensionless. So we define capital X, which has nothing to do with the operator capital X, which is k times L over 2, and Y, which is kappa times L over 2. So these are dimensionless. And notice they're also positive by definition. Okay, because when we take the square roots of these quantities, we're assuming we're taking positive square roots. And then we had, well, first of all, we had looked at the case where V0 was infinite and solved that problem. But then we went back to the case where V0 is not necessarily infinite. And we had first considered the case that it was an even function. So for psi of x even, which means it's equal to psi of minus x.
Excuse me, Professor. Could I ask, how do we know that these are dimensionless? Are these just defined this way, or did we do some kind of analysis on the units and see that L has units of inverse length or something? I would expect it to be just length times length, which would be length.
Thank you. That's because I made a mistake here. The dimensions should be inverse length here. Sorry.
Gotcha. Okay.
Good. All right. Thank you very much.
No problem.
All right. So, then we had written down what the wave function was. I'm going to write it just slightly differently today. So if you're in the middle section where the potential is 0, the wave function is a times cosine of kx. That's if x is in magnitude less than or equal to L over 2. And if you're outside that, then it's a constant times e to the minus kappa times the absolute value of x. That takes into account the fact that the possibility of x being both positive and negative. And that's if x in absolute value is greater than or equal to L over 2. And at the boundary between those two regions, they have to match. Okay, and by match, what we mean is that the wave function and its first derivative are both continuous. Okay, and the reason they're both continuous, well, the wave function is always continuous, but its derivative is continuous only because, in this case, the potential is never infinite. Okay, now, so then when we worked out what that meant, we got two equations. We got one equation which said x times tangent of x has to equal y. And then the other equation really just came from the definitions of x and y, and that said capital X squared plus capital Y squared is mv naught L squared over h bar squared. That's a dimensionless number because x and y are dimensionless. And so what we need to do now to find the energy eigenvalues, which are appearing, they're hidden within k and kappa, which are in turn hidden within x and L, x and y. Okay, and so by solving these equations, we will get, we will be able to find the energy eigenvalues. Okay, so the idea is we're going to look for graphical solutions because otherwise these will be transcendental equations and we won't be able to find a solution in closed form. So we're going to use graphical solutions, which just means that we look at these two curves and we look for their intersections in the xy plane. Okay, and so when I do this, I'm going to graph it with the first equation I'm going to graph as a solid green line, and the second equation I'm going to graph as a dashed blue line. I can get blue here. And so if we look at the xy plane, let me try to make this nice and big. So this is the x-axis, this is the y-axis, and then I'm going to mark it off in units of pi over 2. Here's pi, here's 3 pi over 2, etc. And the reason for doing that is because if you look at the graph of x tangent x equals y, it sort of looks like the following. So it starts at 0 and it asymptotically goes to pi over 2 in x when y is getting very large. So it looks something like, that's not supposed to do that. Looks something like that. And then it starts at pi and it goes asymptotically towards 3 pi over 2. And then it starts at 2 pi and goes asymptotically to 5 pi over 2, sort of like that. Notice I'm only drawing the parts where x and y are both positive. So that's what this looks like. And now these curves are circles. X squared plus y squared equals constant is circles. And so the radius of the circle depends on this quantity, including V0, L, and the mass of the particle. So one possibility is that the circle has a very small radius. For example, if L is very small, pretend that's a circle or a semi part of a circle. But it could have a larger radius, maybe something like this. Okay, but in any case, it's a circle. That curve is a circle. So these are 3 possibilities. Okay, and so we need to find the intersections. If we find an intersection of these two curves, like there, or there, or there, or there, any one of those is a solution to the transcendental equation. Okay, so one thing to notice is that there's always at least one solution because the little circle here always is going to at least intersect with the first green curve. So there is always at least one solution. But there may not be more than one solution. Unlike the infinite square well where we found an infinite number of solutions. So the one solution that's guaranteed to be there is the one that by definition has the lowest energy. And so that's the ground state. So notice that the ground state has to have x between 0 and pi over 2. So it must lie in that range. And if you translate that into what it means for k, that means that 0 is less than k is less than pi over L. And then you can take how k was related to the energy, and you can relate that to the energy. And so what it's telling us is that the ground state energy, the energy eigenstate with the lowest value of the energy, so I'm going to call that E1 for the first one, is less than h bar squared pi squared over 2m L squared. Okay, and that value, the upper bound on it, is what we found if V0 goes to infinity. And if V0 is very small, if we go back up here, we notice V0 is proportional to the radius of the blue dashed circle. So that's saying if V0 is very small, the circle is very small, and the intersection point will be very small. And so the lower bound of 0 is corresponding to V0 very small. And for things that are neither very large nor very small, you're somewhere in the middle. Another thing that happens if V0 is very large, then your circle has a very large, your blue dash circle has a very large radius. And so you're going to have lots of solutions, because if V0 is very large, you have lots of places where you're intersecting with the green curves. You'll be intersecting with a very large number of different green curves. Okay, so as V0 goes to infinity, the radii, or the radius of the circles, or the circle, I should say, increases. And so you get more solutions, and those solutions in the limit are the ones we already found last time. Okay, but for any finite V0, you only intersect with a finite number of green curves. And so you have a finite number of bound states. Okay, so let's talk again about the limit of very small V0. Okay, so for very small but not quite 0, V0, then you get a very small circle, and let's try to estimate the bound state energy in that case. So first of all, there's only one solution in that limit. Oops. Okay, with both x and y very small. And so when we write down the equation x tangent x, that's equal to approximately just x squared. Tangent x and x are very equal, or very near to each other when x is small. And that's supposed to equal y. So now if we plug both of that into the other equation, we're getting x squared plus y squared, which we now see is approximately x to the 4th power, is approximately mv0 L squared over 2 h bar squared. And that's a quadratic equation. So you can solve it for x squared, and you find the result that x squared is approximately mv0 L squared over 2 h bar squared minus the same thing squared. Okay, plus higher order corrections. Okay, and if we want to put that in terms of, back in terms of k, so recall that k squared is 4x squared over L squared. And then we can relate that to the energy. So the energy is approximately, well, actually the energy is exactly equal to h bar squared k squared over 2m. But now what we found is that's approximately, if you plug in for x here, that's approximately v0 times 1 minus a correction. And the correction is m v0 l squared over 2 h bar squared. Okay, and then there are corrections to that we're neglecting. Okay, so that's the energy of the ground state in the limit, which is the only state in the limit that v0 is very small. And you see that to first approximation, it's just the same thing as v0 minus a small correction. And so the implication of that is that this is just barely a bound state. In other words, its energy is just a tiny bit smaller than the potential that we put in. The borderline between a bound state and not a bound state would occur if the energy was exactly v0. And so for any finite v0, it's a little bit smaller than that. Okay, any questions on that so far?
Sorry, Professor, I fell behind. You mentioned that's the energy when the bound state is very small?
When the potential v0 is very small.
Oh, okay.
Yeah.
Okay. Thank you.
Good. Okay, and so all of that was for the case where we were looking at even wave functions. And now we can look at the case of odd wave functions. Okay, so that means psi of x has to equal psi of minus x with a minus sign in front. And if you look back at what we had before, that means that psi of x, psi of x can be written in the following form. It's c e to the kappa x if x is less than minus L over 2. It's a sine kx if absolute value of x is less than L over 2. Oops, this should be a greater than or equal to. Let me fix this. Okay, and it's minus c e to the minus kappa x if x is greater than or equal to L over 2. Okay, and so now we have different equations that are going to come about from insisting on continuity of the wave function and the first derivative at the boundary point. So the continuity for the wave function itself tells us that a times sine k L over 2 has to equal c e to the minus kappa L over 2. And then we can look at the continuity of psi prime, the first derivative of the wave function. And that tells us a k cosine k L over 2 is equal to minus c kappa e to the minus kappa L over 2. Okay, and then once again, we can demand a solution by taking the ratio of those two equations. And what we get is k cotangent of k L over 2 is equal to minus kappa. Okay, so the big differences are, first of all, there's a minus sign that came from the fact that this is an odd wave function. And the other difference that we get compared to the even case is instead of a tangent, we have a cotangent. Okay, but otherwise it's still a transcendental equation. And so we can use the same strategy. We define the same x and y, but now our equations are minus x cotangent x equals y. So that's the thing we have to graph. We're going to use a green line for that again. And the other equation is exactly the same as it was before. It's equation for a circle, x squared plus y squared equals m v0 L squared over 2 h bar squared. Okay, so again, we look for graphical, use a graphical method to look for solutions. Meaning we plot both these curves in the xy plane and we look for an intersection. Okay, so there's x, and once again, I'm going to mark it off in units of pi over 2. Okay, and this is capital Y. Okay, but now the green curves look a little bit different. So this one starts at pi over 2 and 0, and it asymptotically goes up to pi. This one starts at 3 pi over 2 and asymptotically goes up to 2 pi. And this one starts at 5 pi over 2 and asymptotically goes up to 3 pi. Sorry about the wiggles there and that. But those are the green curves here. And then the blue dashed curves, blue dashed circles, depend on, again, what V0 is. So it might be a very small circle like that, or it might be a larger circle, maybe something like that. Pretend these are circles, or it might look like that. Okay, and so the number of solutions, once again, depends on how big is V0, because that's how big the radius of the circle is. But now a big difference for these solutions is if the circle is too small, you won't get any solution at all, namely this circle right here. Okay, so for small V0, we don't have a solution. Okay, we need the circle to be large enough. And how big is large enough? We need the radius of this circle to be at least as big as pi over 2 so that it has a chance of intersecting with that first green curve. Okay, so what that means is for an odd solution to exist, we need the radius of the circle, mv0 L squared over 2 h bar squared. Actually, that's the radius of the circle squared, if we look back at the x squared equation. That has to be bigger than or equal to pi over 2 squared. Okay, or in other words, we need the potential to be big enough. In other words, it has to be bigger than or equal to pi squared h bar squared over 2ml squared. Okay, and if it is, then we'll have one solution. Then if it's larger than 3 pi over 2 squared, we'll have a chance of intersecting with this green curve, and then we'll have two solutions. If it's bigger than 5 pi over 2 squared, we'll have a chance of intersecting, we'll get out to this point, we'll have a chance of intersecting with that green curve. And so again, the number of solutions depends on how big V0 is.
Sorry, Professor.
Yeah, go ahead.
Briefly, just scroll up a bit, just very briefly.
Uh-huh.
A little bit further up. A little bit. Okay, thank you, right there. I just missed that up. Okay, thank you. You're good.
Okay.
Yes.
Good. Okay. So to summarize both what we found for even and odd, for very large V0, what are the solutions? The solutions are going to be, if I scroll back up to this picture, for very large V0, the solutions are going to be at the top of the green curve, so way up here. And so you can read off what the x is. It's going to be pi, or 2 pi, or 3 pi. That's for odd. And if we go back up to this graph, When you're very large, it's going to be pi over 2, or 3 pi over 2, or 5 pi over 2. And so they alternate. Okay, and so the solutions are that capital X is pi over 2, or pi, or 3 pi over 2, or 2 pi, or 5 pi over 2, etc. The ones that have a 2 in the denominator are the even solutions. And the ones that do not have a 2 in the denominator are the odd solutions. Okay, and so what we're finding is that K has to be pi over pi times n over L, where n is 1, 2, 3, etc. Okay, and that's what we found before when we directly took V0 to be infinite to begin with. So this agrees with the particle in a box. V0 equals infinity that we found last time. Okay, and so there's an integer, more generally, there's an integer associated with each solution. And note that unfortunately, just the way it works out is that an even wave function corresponds to an odd integer, an odd n, and vice versa. So an odd wave function corresponds to an even integer.
I'm sorry, what do you mean by corresponds here?
I just mean that the even wave functions have odd n, and the odd wave functions have even n.
Okay.
Good. Okay. So we can also make sketches of what these wave functions look like in general. So there's no attempt here to be too precise, especially if my hands are wiggling too much. Okay, but if we graph the ground state wave function, and let me mark off the points L over 2 and minus L over 2 here. Okay, so the ground state wave function has a cosine form in the middle, and then pretend that's symmetrical. And then as you go off to large X, it's falling exponentially. And again, the first derivatives of the wave function have to match at the join points at L over 2. And so this is the n equals 1 state. And so I've attempted to draw that smoothly, but that's what it looks like. The n equals 2 state, so this is ground state. Then we can graph the n equals 2 state, which goes negative. So this is going to be n equals 2, otherwise known as the first excited state. Okay, and so between L over 2 and minus L over 2, this is a sine function. So it's going through 0. And then it comes up here and it has a, oops. Sometimes my pen decides it thinks I want to draw a straight line when I don't. Okay, so it looks something like that. And then outside, it again decays exponentially. Okay, so that's what the first excited n equals 2 state looks like. For n equals 3, so again, I'm making special points at L over 2 and minus L over 2. Now it's again a cosine in between. So it looks something like that. But then outside, it decays exponentially. Okay, so what I'm graphing here in each case is the wave function. Okay, and so this is the n equals 3 case. And then finally, let's just do n equals 4 just to show what it looks like. So n equals 4 is a sine function, but it's got one more wiggle to it. It's not a very good sine function. Yeah. Pretend that's a sine function. And then outside it decays exponentially again, like so. Okay, so some things to notice is that in general, the number of nodes, meaning the number of zeros, or it's the places where psi of x equals 0, is equal to the integer n minus 1 for each state. So in particular, the ground state has no nodes. That's a general feature of quantum mechanics. More nodes equals higher energy. Okay. And there are never any nodes outside of the well. So no nodes or even any wiggles outside of the well, which means for absolute value of x greater than or equal to L over 2. And that's because it's an exponential function. Exponential functions don't have zeros, and they are monotonic. So they're pure exponentials. And this is true for bound states. Okay, now we're not going to talk about non-bound states for a while, but just to let you know that this changes a little bit if you're talking about states that are not bound states. Okay, so but for energies greater than the potential well, greater than V0, now there are no bound states, or these are not bound states. And so the energy eigenvalues are not going to be these discrete things associated with integers. Instead, they're going to be continuous. Energy eigenvalues are continuous. And if you graph what the wave function looks like for one of those continuous eigenvalues, it's going to look like the following. So this is again going to be psi of x versus x. Here's L over 2. Here's minus L over 2. And so inside the well, the thing is going to be a sine or a cosine, maybe like this, but it's going to be wiggling really fast. Pretend that's a cosine function. And then outside, it's still going to be wiggling, but just not as fast. So it'll look something like that. Okay, so now for non-bound states, you do have nodes and wiggles outside of the well, and the energies are continuous. Okay, questions on that?
Dr. Martin, does the amplitude of the wave change when you get out of the bound state here?
Let's see, that's a good question. Yes, I believe the answer is yes. But so one thing is, because the energies are continuous, you can take linear combinations of them. And so, but I believe the answer is yes. So this should have been here. This should have been a smaller magnitude than that. Whereas all of these within the well should have had the same height. So if my artwork was better, these would have all had the same exact height.
Why would the one on the left have a lower magnitude?
It shouldn't. If I graph these correctly, that it should have been symmetrical. So
Oh, okay.
that and that should have the same height.
Oh, okay. I thought.
Yeah, my artwork is highly suspect.
But so the reason those are lower in amplitude is because they have less energy, or is there a different reason why?
So in some sense, there's less probability to find yourself outside of the well, or a higher probability that you'll be inside the well.
So that's why it would have a lower height.
Yeah.
Okay.
So we'll probably come back to this at some point in the future, but the strategy for the course is to first learn everything we can about bound states, and then we'll come back to unbound states later. In fact, there's a good chance that won't happen until the second semester, 661. Okay, other questions? All right, so now we're actually, compared to where we are in the notes, we're going to go backwards a little bit, and we're going to talk about translations. So let me just first say some preliminary reminders. So we've already said this, but recall that if you have a unitary operator, we said before when we were talking about bases, a unitary operator is something that changes your basis. Okay, and so what that means is, if we transform all vectors in the space, let's just give two of them, for example. So if we have vectors psi and chi, that should have been a chi. And we transform them according to psi turns into the unitary operator acting on psi, and chi turns into the unitary operator acting on chi for some fixed unitary operator. Okay, then this is called an active transformation. That's just the word we use to describe it. But the point is, now if we look at matrix elements, which are related to the things we actually compute, like probabilities and expectation values, if we look at a matrix element, chi a psi, for some observable, that will transform into chi u dagger a u, just plugging in the previous lines, times psi. And so we see that we could have done the same thing if we didn't transform the states, but instead transform the operators. So this is the same as transforming all operators. According to the rule that any operator goes into u dagger times the operator times u. Okay, and you leave the kets and bras the same. Okay, and that is called the passive view of the transformation. And we're about to apply this to the special case of a translation. Okay, so to do that, let me just tell you, let's just define the translation operator. This is a particular kind of transformation. And so I'm just going to define it according to, I'm going to call it T for translation. It depends on a number A, and it's defined to be e to the minus IA momentum operator divided by h bar. So if you're exponentiating something, the something has to be dimensionless. And that tells us that because we know the dimensions of momentum, that's telling us that A is actually a distance. Just to make this thing work dimensionally. And we can define what the exponential of an operator is by expanding it in a series. Okay, so we can think of this thing always as the sum from n equals 0 to infinity, minus IA over h bar to the nth power, momentum operator to the nth power over n factorial. That's the definition of the exponential function. Okay, and by doing that, we then realize that TA is unitary because P is Hermitian. Okay, and so what that means is if we take the Hermitian conjugate of TA, that's the same thing as the exponential Hermitian conjugate. And we just Hermitian conjugate every term in the sum. That's going to take our minus I and turn it into a plus I. It's not going to do anything to A. A is a real number. It's not going to do anything to P because P is Hermitian. Same thing for H bar. And so this is equal to, that's the Hermitian conjugate. So from that, we learn that the inverse of TA is equal to the Hermitian conjugate of TA. And by the way, it just flips the sign of A. So that's the same thing as T of minus A. So that's one thing we learned from this. Another thing we learned from this is also TATB is just the same thing as T of A plus B. And the reason for that is because P is the only operator involved here, and any operator commutes with itself, so we can just pretend it's a number for the purposes of seeing how these things work. And so then the exponentials just obey. This is just how exponentials behave. Okay, so now we can go back and use a result that you proved for homework. So this was homework set 2, problem 3. With, in the problem, you take A as X, and you take the operator that was B in the problem as P, and then their commutator is IH bar, which is a number, so it commutes with everything. So it satisfies the results of the problem. And if you plug that in, what you find is that if you compute the commutator of the operator X with the translation operator for A, that's IH bar times minus IA over H bar times e to the minus IA P over H bar, which is the translation operator back again. So this is A times T of A. Okay, so that's a consequence of that homework problem. Okay, and if we just rewrite that, we get operator X acting on TA is equal to TA acting on the operator X plus A times T of A. A is just a number, so it commutes. Or just rewriting it, this is T of A times the operator X plus A. Okay, or now we can multiply both sides by the inverse of TA, and so we get TA inverse, which is the same thing as TA dagger, multiplied by x multiplied by TA is equal to x plus a. Okay, and now that we recognize as a passive view transformation. And so this is in fact a translation by a distance a in the passive view. Okay, and so one way of thinking about this is if I have a number line in one dimension, okay, and I mark off some number of units of this, and let's say my particle is sitting there described by a coordinate x, and now I shift it to the left by a. So this is moving coordinate system to the left by a. And this is the before picture. And this is the after picture. Okay, so I mark off things. My particle is still at the same place, but now I've shifted it by a. And so now its new coordinate is x plus a, is the new coordinate we use to describe it. Okay, so passive is saying that you're not actually doing anything to the particle. You're just doing something to the coordinate system that describes the particle. And you're moving the coordinate system, you're shifting it to the left by a. And that means anything described by an operator x is now going to be described by an operator x plus a. Okay, so now we can relate that to the active view by the following trick. So let's say we act on this, we act with this operator relation that we've derived on a position space basis ket, or a whole set of them. Okay, so we have TA, let's write it as dagger this time, just for fun. Okay, that acting on an eigenstate of position is equal to x plus a acting on the eigenstate of position, which is easy to evaluate because now the operator x just turns into the number x, since we're acting on its eigenket. Okay, so this was an operator. Now it's become a number. Okay, and now we can act on both sides with TA, and we get x TA acting on the ket x equals x plus a, the number, TA acting on the ket x. And if I put parentheses around the TAX's, that's telling me that TAX must be a multiple of an eigenstate of x plus a. So in other words, it must be x plus a the ket, although it's possible it could have a phase. Because any phase times the ket x plus a would still be an eigenstate with eigenvalue x plus a. That's the ambiguity that always occurs when you're solving an eigenvalue problem. Okay, so it must be true that this is valid for some theta, but there's no way to know what the theta is, and so we resolve the ambiguity just by choosing it. Okay, so we resolve ambiguity. What else should we choose but theta equals 0? That's the nicest choice. It will lead to the fewest problems. And so we just make that choice. And so what we've learned is that our unitary translation operator acting on the ket x is equal to the ket x plus a. Okay, and so that's the active view version of the transformation. Okay, and here we're basically our operator is sort of physically moving the particle, actively moving it. So the operator TA moves, if we think in terms of states, it moves, I'll put this in brackets just to delineate it, the state in which the particle is certain to be at X with maximum probability into the state where it's certain to be at X plus A. Okay, and so instead of moving the coordinate system, we're moving the particle itself in this version. Okay, and so other things that are true that follow from this are that the bra X plus A is equal to the bra X multiplied on the right by TA dagger, which is the same thing as X T minus A, as we noticed above. And so it's true that if we look at X TA times any state psi, that's equal to X minus A psi. Okay, and that tells us our transformed wave function is psi of X minus A. So that's the difference between the active view and the passive view. When you have the active view, your wave function argument is getting shifted by subtracting A, which corresponds to moving the coordinate system to the left by A, which is the same thing as in the passive view, moving the operator to the right by A, taking it X to the A. Okay, so next time, we're out of time for today, but next time we will talk more about what this means, and especially for situations where you have a invariance under translations, which is not always. And also we'll talk about similar transformations for parity and rotations. Okay, so that's it for today. Are there any questions?
I have a question.
I have a question
Okay.
as well. Samana can go first. Samana.
You can go ahead. You can go ahead. It's okay.
Okay.
Okay, I guess. About that second line there, second from the top, you have X times the quantity TA ket X.
Yes.
How do we make the substitution of X goes to parentheses X plus A?
Sorry, let's see.
Like, how does the left become the right side of the second line there?
Oh, so what we did here, maybe I should have written this here. So now on the previous line, we act with TA. Okay. So
we act TA on the X
we
operator.
act on this whole equation right here. So when we act on that, the TA acting on the TA dagger just gives 1. And so it just goes away. And we're left with X TA X, which is this. Okay? And acting on this, the other side of the equation, since this is just a number, we can put it wherever we want. So I've chosen to put it there. And then what's left is the TA acting on the X. So that's what this is.
Oh, you act on the left side of the equation with TA.
Yeah, we're acting on both sides of the equation with TA. We have to act on both sides of the equation to be fair.
I mean, sorry, we act on the left side of each side of the equation. We put a TA on the left of the left-hand side, and we put a TA on the left of the right-hand side.
Correct.
Is that correct?
That's correct.
Okay, and that commutes with small x plus a, so you're able to switch them.
Exactly, yes.
Gotcha. Mainly when it comes to doing the homework, I'm just always confused about what commutes and what kind of moves like that are legal. So getting these kind of clarifications is helpful.
Yeah, so numbers commute with everything.
Yeah.
And so you can move them wherever you want. And that's why that's often the usefulness of doing, for example, a completeness relation. Is a lot of times when you do a completeness relation, the reason you're doing it is to change and turn an operator into a number, which you can then move wherever you want, and then you can undo the completeness if you want. So if you're wondering why is it that completeness is often the key to solving a problem, that's one of the reasons. Changing operators into numbers is often useful.
Makes sense. Thank you.
Good. Maybe I should stop recording here before we run too long.